blunder when brewing your buffers. So buffers are pH stabilizers, and there are different buffers that we can use, and the ones that we use depend on like what pH we're trying to stabilize, and as well as other things like whether the component of the buffer might react with something in our experiment. And so there are different reasons to choose different buffers. So today I wanted to tell you more about why you might want to choose different buffers for different experiments, how you choose a buffer, as well as how you prepare the buffers. There are heaps of buffers. We're talking heapies, tris, mops, chaps, pipes. I can't even remember all the different names, but there's a lot of different buffers. But you can narrow things down, and you can start narrowing things down by finding a buffer that has a pKa that is near the pH that you want, so that you're in the buffering zone. Okay, that was a lot of jargon, and so more on in yesterday's post, but basically pH is a measure of the level of protons. You can think of it kind of like a proton jar, kind of like you have a cookie jar. The more protons are in the jar, the more acidic the solution is, and it's an inverse log relationship. So the more protons there are, the more acidic it is, the lower the pH. The fewer the protons there are, the more basic it is, and the higher pH. The point with a buffer is to keep the proton level constant. And in order to do this, you need to be able to counteract any outside like forces. So if an acid comes in and drops a proton, you need a base that can come and remove a proton, because an acid is something that donates a proton and a base is something that removes a proton. So if you have an external proton added, then you want your buffer to be able to act as a base and take that proton. If you have an external acid that is going to an external base that is going to take a proton, you want your buffer to have an acid that can donate a proton, so that your proton level stays constant, your pH stays constant. In order to do this, your buffer needs to have about equal amounts of the acid and the base form. And so you can do this by buffers use what we call like weak acids. So a weak acid can donate a proton and it can take a proton. And so once it donates a proton, now it acts as an acid, it donates its proton, now it's the conjugate base which can accept a proton. And so with like a strong acid or a strong base, it would only do like one. So a strong acid would only donate, and then it's like, no, I'm not taking it back. A strong base, it would only take, and it's like, I'm not giving this back up. But a weak acid can give and take. It can go both ways. And with a buffer, you want to have about equal amounts of both, so that you can counteract any added stress to the system in order to keep the pH constant. So in order for this to work, you need to have about equal amounts of the acid and the base form of the weak acid. We typically use this notation HA for a weak acid, and then this can deprotonate to form H+, which typically links up with water to form a hydronium ion, H3O+, because protons just don't like to just like hang out as is. Plus A-. And so this is your conjugate base, and this is the conjugate acid. We can define a value called a pKa, which is the pKa, so at the pKa, concentration of HA equals the concentration of A-. So basically you have equal amounts of your conjugate acid and your conjugate base. So these brackets just mean concentration of. And so the pKa is the pH at which this happens. So you can think that above that you have fewer protons available, so you're going to have more in the base form. Below the pKa, you're going to have more protons available, because remember that means the solution is more acidic, and so you're going to have more in this protonated form, in this conjugate acid form. But around this pKa, so at the pKa you have equal amounts of both. If you go plus 1 pH unit, so you're getting more basic, now you're going to have 10 times more base than acid. And if you go -1, you're going to have 10 times more acid than base. And so there's this thing called the Henderson-Hasselbalch equation that is where all these numbers are coming from, and more on that later in the post. But I just wanted to give you this idea of why. So if you were to go like 2 pH units, you'd go 100, 3, you go 1,000, and so you can quickly get out of the buffering range. So we want to choose a buffer whose pKa is within about plus or minus 1 pH unit of its pKa in order to ensure that we have enough acid and enough base to counteract what's going on and if you add or take a base from here, so that you can maintain these constant levels. Because if you go too far away from the pKa, you're going to have, if you go too much further, like higher in pH, so more basic, you're going to have almost all of your buffer will have been deprotonated. Or if you have more basic, yeah, almost all of it will be deprotonated, and so then you don't have the protons that can then add. You're not able to counteract added base because you just don't have enough of those molecules. Whereas if you're too far below the pKa, so you're too acidic, now you have it like all in this acid form, and so you don't have anything that can be taking if there's another acid adding things in there. It can't keep up with removing things because it's already all used up.
This is an example of a common buffer that's used in biochemistry, tris, and so it has this amine group, which can cause problems with like if you're trying to do cross-linking or something, and that's amine sensitive. But it can be in this protonated form, or it can deprotonate. And so this is its conjugate acid. It loses the proton, it becomes its conjugate base. When it's above the pKa, that means that so when the pH is above the pKa, there aren't as many protons available. And so more of it's going to be found in this conjugate base form. Whereas below the pKa, there are more protons available. And so more of it's going to be found in its conjugate acid form. At the pKa, you have equal amounts of both. And this is why the buffers are really good around the pKa of the acid. Because if you go too far away, you're not going to have enough of the base to counter any added acid. And if you go the other direction, you're not going to have enough of the acid to counter any added base.
When we're preparing a buffer solution, we need to prepare it so that it has like roughly equal amounts of acid and base. But remember that that's related to the pH through the Henderson-Hasselbalch equation. So there's only a certain range of pHs that each buffer will work for, depending on its pKa. But we can tweak things a little bit by adjusting the pH, such as by adding more of the conjugate acid form or adding more of the conjugate base form when we're preparing it. Or by, so instead of adding like a 50-50 mixture to start with, we start with slightly more of the acid form if we want a lower pH, and slightly more of the base form if we want a higher pH. Or we can prepare a buffer by starting with only one or only the other, or like a mixture of both, but then adjusting the pH by adding an external acid or an external base. So something else adding in the protons or whatever, so we can kind of like do some of the work for it in order to get it where we want, so that it then still has plenty of the acid and the base form to do its job without having to use up its own acid or base. So typically there are different ways you can prepare buffers, and so it'll depend on the type of buffer. So sometimes you'll prepare like solutions of like the acid or the base form and then like mix them, or you'll mix like amounts of the base and the acid form to try to get close to the pH you want. Or you'll just start with one, like either the base form or the acid form in like make a solution of that and then adjust the pH. And so that's the form that I will be showing you, but most of the stuff I'm going to talk about is going to be relevant for anything, because you're almost always going to have to adjust the pH even if you calculate it out. So there are a bunch of like tables you can find online and calculators, but at the end of the day you're probably going to have to adjust the pH in order to get it right where you want. So you can adjust the pH by like adding a strong acid. So remember, a strong acid is something that's just going to donate its proton and then like okay, we're good. A strong base is something that's going to take a proton and then be like, okay, we're good. So those you don't have to worry about like going back and forth. So they're only going to contribute one way. So they're going to like donate a proton or they're going to take a proton. And this is going to help tip the scale of the proton jar so that the buffer still has enough of its things to do its buffering. And so for the strong acids, if we have like a buffer that already, we want to use, so when we're adding like an acid or a base, so such as like HCl, hydrochloric acid, or sodium chloride, sodium hydroxide, NaOH. We want to add, so you can see that those have like a carrier ion. So basically the H plus part of the HCl is what we care about. We want the proton. The OH minus part of NaOH is what we care about. We want that hydroxide ion. But we need that counter ion to make this like neutral salt that we can add, or this solution that we can add. And so we want to make sure that that counter ion is something that's already going to be in like the buffer that we're going to use it. So if we're making like, if we plan on using this buffer with like a sodium chloride, because we're not going to use this buffer like as is. We're typically using it as part of a lower dilution of it as part of a solution. So if you're going to use it with a buffer that has like NaCl in it, then you would use HCl, and that works fine. With the base, you like, if you have a potassium solution, you can add potassium chloride, potassium hydroxide instead of sodium hydroxide, which you would use if you were using a solution with sodium, but you don't want to have to adjust the pH too far, because then you're adding in a bunch of external ions. So you're adding in like all those salt molecules, especially if you're like overshooting it. So you're adding HCl and then you're adding NaOH, and now you've added salt, and now your solution's super salty. And so there's this thing called like Ionic Strength, which has to do with how many ions or charged particles are in a solution. And so you don't want to be like super duper increasing your ionic strength, because that can, it kind of makes this like molecular fog, where it's hiding the charges and making it harder for charged molecules to see each other, because now you have all these external charges in there. So you want to, that's why it's good to calculate ahead and like prepare your the concentrations that you're going to add in order to get close to your desired pH, and then you can make those slight adjustments without having to make like major adjustments that are going to like crazily salt up your solution. We'll be able to adjust the pH a little within that buffering range of the buffer that we choose, and I'll show you how later in the video. But we need to make sure that we're within the buffering range of that buffer. So we need to, that's where that pKa comes in, is really important when deciding what buffer to use, is that buffer's pKa and its buffering range. But that's not the only thing that's important when you're trying to decide what buffer to use. Different buffers have different strengths and weaknesses that are sometimes totally unrelated to the strength or weakness of the acid within them. Instead, they can do things like cause problems if you're using metals, or if you're different detection methods. And so I want to tell you a little bit more about some of the commonly known contraindications for using specific buffers, and things to keep in mind when preparing certain buffers that might be more like finicky and sensitive. And then I will show you how we actually do it in the lab. We're talking like dissolving things, stirring things, filtering things, you name it. And so yeah, so first let's go talk about how we decide which buffer we're going to use. Oh, and then at the end I'll get back and show you some of the number stuff with the Henderson-Hasselbalch, and also show you some resources where you can find more information about preparing specific buffers, and charts with like the pH and pKa and all that stuff. And so hopefully this post will help you.
When you're choosing a buffer, its most important thing is first you want to find one that is in like the pKa is near your pH, desired pH. But then you also need to make sure that it's not going to be incompatible with your experiments. And you need to make sure you prepare it correctly. So in terms of like compatibility, there are some common problems to keep in mind, is that like buffers with phosphate, so think about your PBS, your phosphate buffered saline, sodium phosphate buffers. These and citrate containing buffers can chelate metals, so they can basically like snatch metals and hold on to them. So there's a few problems with this. One is that when they're doing this, they're binding to the metal, so metal like cations are positively charged. So these the buffers, they're deprotonating in order to, like, they're binding in their deprotonated form. And now you're kind of like pulling the equilibrium and you're taking out this deprotonated form, so more of the phosphate is going to deprotonate. That whole like Le Chatelier principle you might have learned about in general chemistry. So you are deprotonating this phosphate, and so that's going to lower your pH. And so if you don't have metals in your like stock or whatever, and then you're in a solution with a bunch of metals, now you're going to be driving down the pH. Also, if though there were like enzymes that needed those metals and now you are hiding those metals, that could be a problem. And it can also cause salts to precipitate if the salts are like insoluble, like calcium phosphate, or I think calcium citrate or something. I don't know. There's some of them that are insoluble, and that can be a problem. You also don't want to use phosphate containing buffers if you're using like an alkaline phosphate detection method. So for some of the Western blotting, some of the protocols, the detection methods for like the antibodies use alkaline phosphate detection method, and if you have phosphate in your buffers, that's going to be a problem. Some other problems, you don't want to use tris or glycine containing buffers if you're doing amine-based cross-linking. So if you're using like NHS esters or glutaraldehyde, formaldehyde, all these various things, they're going to interact with the cross-linker, and that's going to cause problems. Tris and keepies will react with Depsi. So that's a chemical that we add to, we like pre-treat water with in order to make it RNA free. And then we autoclave it to like inactivate the Depsi so it doesn't cause other problems. But you can't do, the Depsi is going to interact with the tris or the heapies. So if you want to use one of those types of buffers in your reactions, make sure that you do the Depsi, all of that stuff, like do that first. Like you don't add Depsi to a buffer that has that. Speaking of autoclaving, mops can't be autoclaved, so don't try. Then there could be other like known issues. Like some of them will absorb like UV light or light at a wavelength that you're trying to use to measure something. Some of them will bind to DNA. So there's various problems, and so they're really great guides online, really laying out all of the pros and cons of the various buffers. But no matter what buffer you choose, you need to make sure that you're preparing it correctly. And so some of them are more finicky about making sure you really prepare it correctly. And so one of these is tris. And so tris's pH is temperature sensitive. So at a higher temperature, it's going to be easier to deprotonate. It's going to be more willing to deprotonate. So that's going to make your solution more acidic, meaning that your pH is going down at a higher temperature. And so that means at a lower temperature, your pH is going to be higher than you expected. And so you want to make sure that you're preparing it at the temperature that you're planning to use it. Also note that large dilutions can affect the pH for like tris, and some of them, not for all buffers, but so you don't want to make really large dilutions, or if you do, you want to make sure that the pH is still okay.
So one of the most useful things I could tell you is to make stock solutions. So like 1 molar is really, really useful because you can easily see when V1 down to like, so if you wanted a 500 millimolar, then you would so if you wanted like a 50 millimolar in 1 liter, that would be 50 mils of this, and then you fill it to a liter, and 25 would be 25 and that sort of thing. And then if you only have 500 mils, you have that in your head, so you can do some easily mental math. But in addition, having a high concentration stock solution, now you don't have to dissolve out that acid and base every time that you want to make a buffer. So you have to do one in your stock, but when, like, most of the time we're not going to use just like the buffer as is. Like we would never put our protein just straight in this. Instead, we put it in like a solution solution with salts and the various things that the protein might want, and at a much lower concentration of the buffer. And so by making these stock solutions, we can then have more easily make these buffers that we want for our proteins, and so like our working buffers type of thing, instead as opposed to like the stock solution. But the actual we tend to call like just like any solution that has a buffer in it a buffer, even if it's not like just the buffer. So it's really important that when you're preparing your buffer, you leave room to adjust the pH. So typically I will like dissolve the solids. If it's one that I'm making from solids, I'll dissolve the solids in like, so if I want to make a liter, I would dissolve the solids in like 700 milliliters in like a beaker with a stir bar, and I'd put this on the like on a stir plate with the pH probe above the stir plate. So you can set it up kind of like this with your probe, and that would be in the buffer, in the solution as it's mixing. You don't have to do this like until it's actually like dissolved or all the other way. But sometimes actually some buffers you want to look, because sometimes they won't dissolve until the pH is like acidic or basic enough. So you might need to actually like add some base or some acid to try to get it to dissolve. So you can do the buffer preparation in different ways. So you can start with adding some buffers you can start with like adding the base form and the acid form. So with like tris, you have tris base and tris HCl, so tris hydrochloride. So this is the acid form and this is the base form. So if we were to dissolve like just this, so just the acid form, I think there's a pH, like a 50 millimolar solution or something would have a pH of 4 point something. And then this would have like a pH of like 10 point something. And so this is going to be too high for what we want, and this is going to be too low for what we want. So if we start with just one of these, we're going to need to adjust the pH. So you can calculate how much of each you need to add in order to get to a desired pH. But in practice, what we typically do is just make it from the base and then adjust the pH down. We adjust the pH from the tris hydrochloride, so now we already have chloride, and then we're going to add NaOH. So when you add NaOH and you already have HCl, now you're going to be increasing the ionic strength more than if you start with the base and then add HCl to get down to where you want to be.
For just a basic one where you're making it from a base, you want to weigh out what you'll need, which you can calculate using dimensional analysis with your molecular weight or your formula weight and the desired concentration.
It's also important to note that tris base and tris HCl, sometimes called Trisma, I think it's like a brand name. So those have different formula weights. So with the HCl, it's 157.6 grams per mole. With the base, it's 121.14 grams per mole. So you can see that when you have the acid form, then you're coming in with the HCl, so it has each like the same amount mole-wise, so the same amount of like molecule-wise is of the tris is going to weigh more because it's coming in with all that other stuff. And so you need to be careful that when you're determining, like calculating how much you need to add for a certain molarity, that you're taking into account the actual molecular weight of the form that you're adding. So you dissolve your solids in here, or if you're like mixing different liquids or whatever. But basically you're going to want to leave room to adjust the pH. So even if you try to calculate beforehand to have the right amounts of the various solids like that you would need, it's probably going to be a little off. And so you're going to want to adjust the pH. And so you want to leave room to adjust the pH. So remember that the markers on these beakers are only approximates. So you don't want to like rely on them. But you also, they can be helpful for this part because you just want to make sure you leave enough room to adjust. And so you adjust, you can adjust with the pH probe. And so you want the probe in there and you want it to be mixing while you're doing this. So you have it like the stir bar. So it's mixing the magnetic stir bar on the bottom. It's going to be mixing the liquid as it goes. And you have your probe in there. And so what you'll notice is you can add like NaOH, either pellets or a concentrated solution dropwise. Sometimes if it's like way off, you can like, it'll be way off. You're going to need to add a lot of base and stuff. It's easier to add the pellets, but then as it gets closer, you can add dropwise with the concentrated solution, because that's easier to add small amounts. So when you're doing getting to the right pH, you'll find that if you're in the buffering region, you'll feel like you're adding oodles and oodles of your acid or your base, and it's just like barely changing. This is because you're in the buffering region. But getting to the buffering region, the changes will be a lot faster. And because you're not in the buffering region, you're not buffering, you're just gonna be, so you're gonna wildly be changing the pH. And if you're on the edge of like the buffering region, you can easily like switch out. So you can easily switch into and out of the buffering region. So you need to be careful about that. So you don't just like get really impatient. Like I've been adding oodles and oodles and it's not changing. And then all of a sudden you add oodles and then you way overshoot it. And then you have to add like the base of the acid or whatever to go back the other direction. So be aware of that and be patient. So sometimes it takes a while for it to stabilize. And so you want to make sure that the pH stabilizes. So typically I'll get it to the pH I want, and then I'll actually like just let it sit there for a while and make sure that it's actually stable at that pH, because sometimes it'll like waver a little. When you're adjusting the pH, it's important to note that you want to adjust the pH at the temperature that you're going to use it. So for some buffers, especially tris, this can be a really important thing, that the pH is actually going to change when you change the temperature. And so with tris at a higher temperature, your solution is going to be more acidic, so it's going to have a lower pH. This is because the bond holding the proton onto the tris that it's going to donate, so that bond is actually, it has a higher enthalpy than like the bonds that are going to deprotonate for other buffers. And what this means is that you have to put more energy in to get that H to come off, get that proton to come off. And heat is energy. And so the more heat you add, the more likely that is to happen. So if you were to cool that down, now your deprotonation is going to be slower to a lesser extent, and you're going to have a more basic solution, so a higher pH at a lower temperature. And so it's important that especially if the pH is sensitive, you want to make sure that the pH is where you want it at the temperature where you want it. Once you have it at the right pH that you want, you're going to need to adjust it to the final volume that you want. And so here's why it's important that you leave enough room, because if you ended up having to super adjust the pH, then your volume is going to increase. And so you pour your solution into a graduated cylinder, which is actually a measuring device, as opposed to a beaker, which is good for like.
And make sure that when you don't like pour in the stir bar. So if you have like a magnet, you can hold the magnet on the bottom of the beaker while you're pouring, and so it doesn't like fall out.
But so you want to fill it up to the line. Remember that it's the bottom of the meniscus that you want on the line. So the bottom of the smiley face, that's where you read from. So that should be on the top of the line. And then typically what I do is I vacuum filter the solutions into a bottle. So I've showed you that in a past post, where we have these contraptions that we can stick on top of a bottle, and then there's a filter and you put it through. Because so when you're making a buffer, you want this to be like stable for a long time when you're making like a stock solution, or even if you're not making a stock solution, you still want your buffers to be stable. So you want to like filter out any like the contaminants that are going to mess you up.
Here's that Henderson-Hasselbalch equation I was talking about. If you visit the blog version, there's a lot more, and there's a bunch of videos online about this and stuff, so I don't want to try to like explain it too much, but it kind of just makes sense if you look over the math about why this is happening. So at why like a buffer has a useful buffering range is because at that pKa, they have an equal amount of the protonated and the deprotonated. So we often refer to, for like a weak acid or base, we refer to the acid form as HA, and because it has a proton and it loses its proton, it's A minus. That's the conjugate base. And if you go each, so you can see that Tris has a pKa of 8.2 at 20 degrees Celsius and a useful buffering range of 7 to 9. So at pH of 8, if you put it all into that equation, you see that you have about 0.63 of the base, the conjugate base to the conjugate acid. So you still have more acid than base, but enough to buffer. When you go to 7, now you only have 0.063. So this is you're running really low on the ability to buffer. And if you go the other direction, now you have at a pH of 9, you have 6.3 times more of the base than the acid, and so that's going to be a problem because you can't buffer. And so that's why this has this effect. So you can find like a lot of really great guides online, and you can check out all of these different buffers. So some of the ones that we commonly use are like Tris buffers, Hebes, MOPS, but these all have different, you can see that they all have different pH ranges, different pKas, and then they have different comments about like some of the problems with like incompatibility with various assays. And you can also find even more with millipore sigma has a bunch, as well as you can see the effect of the temperature on the pH. And so how at a higher temperature, you're going to have a lower pH, as well as the amounts of the various ones to mix in order to get various solutions. And so there's tons of information online about how to calculate these types of things. And I will put links to these various things, and hopefully they can be helpful for you in the lab.